Hey, this is Horner. We're going to look at 16.2. This is about electric conductors and insulators. Different materials they do vary dramatically in how easy they are or how difficult it is for charge to kind of flow or move within them. So things that have an easy time allowing charge to move through are called conductors, and things that we have a little bit of trouble with charge moving through are called insulators. So you've experienced both of these. Conductors, typically these are metals, and insulators typically are non-metals, although it doesn't always have to be that way. And intermediate between the conductors and insulators, these are semiconductors. So you see a lot of these materials in computer chips. So if you go back to chemistry, you can kind of think about it that way, and kind of how it works out. So let's go on to the next slide. This is showing you how to charge an insulator by rubbing. So we're not charging metals here. We're going to charge things that are non-metals, rubber, glass, non-metals. So when we charge these things, we basically just use friction. So we're going to rub the two together. If I do take wool and I rub it against some hard rubber, if I rub it for long enough, I'll notice that I will have a negative charge on the hard rubber, and then on the wool I have a positive charge. And basically you'll see that here that electrons are removed from the wool and they're deposited, so we're moving the electrons from one object to the other. Glass and wool work kind of the opposite way, and typically what you'll do is you'll have glass and you'll have silk. Silk seems to work a little bit better for this, so we're going to put silk here and kind of put a question mark on the wool. The electrons are actually removed from the glass and they deposit themselves on that silk, or in this case what they have here is wool. And so we can move charges from one thing to the other. And when we do that, we have an excess charge on each one of those objects. If we take a conductor and we want to charge it, typically what we'll do is we'll take a non-conductor like a glass rod, we'll charge it up by placing some charges here on that glass rod. So we've got an excess positive charge. If I take the glass rod and actually touch it to the metal sphere, then it will transfer some of those electrons to the glass rod, which then when I move that glass rod off will make that metal sphere basically have a excess positive charge. So the more I do this, the more positive charge you're going to end up with on this little device. The reason we have an insulating basis on the bottom is if you would take a wire and connect it here, we would say that it would make a ground, and we would then have a discharge, and this would go back to being neutral again. So right here it's neutral. We move some of the electrons off onto the glass rod, move that glass rod off, and when you do that, you end up with an excess positive charge here. For the next section, this is where we're talking about grounding. So how do we discharge a conductor? So if you remember, we in the last video talked about if you're walking across a nice shag carpet, you pick up a lot of different electrons on you, and if I touch somebody else, I discharge. And the reason I discharge is those electrons will travel from my body to that person's body, and then they travel down into the ground. So Earth is a big conductor. There's a presence of ions and moisture. It's large enough that it can be a limitless reservoir of charge. So to ground a conductor, we're basically just making sure that we have a conducting path. So this conductor now is this person between the charge reservoir and the Earth. And so you'll kind of just have to kind of see, oh, anytime you have something charged and it touches the ground, we say it discharges. It has a lot to do with electricity and a lot of things that you do in your home too. Charging a conductor by induction. Induction's a little bit different. We don't need grounding to happen, and I'll kind of show you how that happens here. So you don't always have to discharge it, but looking at this slide, what we have are two metal spheres. They're mounted on insulating stands, typically glass or plastic, and we take a positive item and we get it close to the two spheres. The sphere on the left develops a net negative charge on the left, and the sphere on the right develops a net positive charge. So when I separate the two, that excess charge stays on each one of those two objects. I can also do the same thing using a negative object, get it close to sphere A. So now I have my electrons moving to the other side because the positive charges like to be here. Negative charges want to get as far away as possible from that negative object, pull them apart, and now I have the opposite situation. So pretty easy to do. If I want to ground these or discharge them, all I do is connect a wire from here down to the ground, and when I do that, it will allow those electrons to move off, and then this will no longer have a negative charge. It'll have a neutral charge or a zero charge. Still has charges on it, but they are equal number of charges on both. Here's another way of looking at it. I've got a glass rod, got a silk cloth. I rub the two together. It makes the glass rod positive. I touch it or just get it close to this, and then it becomes charged. And then if I take a wire and connect it, I'll have those electrons will flow from the ground through the wire to the sphere, so they'll actually move up on it. It's even possible to charge an initially neutral conductor by grounding it, so I can do the same type of thing. Here I'm doing the same thing I did up top, and this time what we've done is we've removed the rod. When we remove the rod, you'll see that there's a excess of negative charges on that sphere. In example 16.2, we have something called an electroscope, and basically what it is it's a some sort of chamber so that the air doesn't affect it, and there's a conducting bulb, so that's this piece of metal here, a pole, and then it's connected to some very thin, extremely thin foil leaves. You can use gold, you can use most conductors on this. Gold is really nice. They want to know what happens to the leaves as the following operations are carried out in the order listed. So they want you to explain what you see in each step. So the first thing is you touch the metal bulb at the top of the electroscope with your hand. So negative charged already. If we touch it with our hand, we will ground it. So charge will be transferred. So basically here's your finger. Okay, your finger comes in and you touch it, and all those negative charges will move along your finger, down your arm, and then down into the ground itself. And so now the net charge on this thing is 0. The foil leaves because there's no charge on either one, and since there's no charge there, there's no separation. Remember in the last slide we said that if they are charged, so we'll go back to that last slide, if they are charged, they do actually separate. So here, because we lost that charge and they're both neutral now, you see that those two gold leaves are closer together. If I take a positively charged rod and I get it near the bulb, the electroscope becomes polarized with induction. So what I've done is I've pulled the negative charge up, which leaves the positive charges on the bottom, and these gold leaves hang apart. So you actually see them move apart from each other. For the next part, it says when the negatively charged rod touches the bulb, some of that negative charge is transferred, and now the electroscope has a positive charge. The glass rod still has a positive charge and repels the charge on the electroscope, pushing as far away as possible toward those foil leaves, and now the leaves will hang even further apart because they have more charge. So initially it was just hanging down and you just had the two leaves. We got that close to it and we ended up having these leaves separate a little bit, and then we did the third step and now they really separate a whole bunch. We're just adding more and more charges to them. So here we've only got 2 charges on each one. Here we'll put 3, and the more charges you have, the bigger the force is between them. Here the net charge is 0. For the next section, this is just about how photocopiers and laser printers work. I've put in your notes a pretty lengthy detail kind of how that happens, so you want to make sure that you read through that. But it's basically just electrostatically charging paper and then heating up some toner or some charged particles that have attached to that paper in order to make copies. So it's a pretty ingenious idea pretty simple in concept, but if you've ever worked with copiers, you know that they're kind of finicky. We're going to do some things called quick checks now. These help us just to kind of think about what we've learned to see if we can remember what's going on and if we can apply it. So here I've got a charged glass and a charged plastic rod, and they're hanging by threads. An object attracts the glass rod. If the object is then held near the plastic rod, what will it do? Will it attract it? Will it repel it? Will it not affect it at all? Or either A or B, there's just not enough information to tell. And if you think about it for a second, you can always pause the video, write down an answer, and then come back. And I'm going to go ahead and give you the answer now. And the answer here is either A or B. So this object could have the same charge as that plastic hanging rod, and that would repel it. Or it could be neutral and it would attract both of those rods. So here, let's say that the glass rod, we'll make it positive, like kind of what we've done. And then we'll make the plastic rod, let's make it negative. So if the plastic rod, if we've got this thing that's charged, and let's do this one in red, let's say it says that an object attracts the glass rod. So if it's negative, if it's a negative object, it will attract that glass rod, okay? If it's negative, we know that it will also push away, okay, so these will go in opposite directions, that plastic rod. But if this thing is neutral, so if it's neutral and it doesn't have any charge, what'll happen is it will develop a polar charge on it. It might be polar, have negative charges on the left and positive on the right. If that's true, it would attract the glass rod, but it would also attract that plastic hanging rod. So our answer here has got to be either A or B. There's just not enough information for us to really figure out what's going on. Rod attracts a positively charged hanging ball. So after we've done the last one, the rod can be, so is it positive? No, if it was positive, it would repel it, so that cannot be the right answer. How about negative? Well, if it was negative, then yeah, it would attract that ball. So that's got to be one of the answers. How about if it was neutral? So let's say that it had both positive and negative charges. So positive, negative, positive, negative, positive, negative. If you got it near the ball was positive, what would happen? Well, if we go back to kind of what we were thinking about, we know that the negative charges would move to this side and the positive charges would be then left over on this side. And so this neutral rod becomes polar and it would also attract. So because both B and C are the answers, you're going to have to pick either B or C. It can't be both. It's either going to be neutral or negative, but those are two very valid answers for this question. 20.4, there is no 20.3, so 20.4 says metal spheres 1 and 2 are touching. Both are initially neutral, which means they both have positive and negative charges, but equal amounts. I have a charged rod. It is brought near. When it gets near this first sphere, the electrons or the negative charges are pulled to this side. Okay. Now we have an excess positive charge on this side. We then remove the rod, so now the rod goes away. The instant that that happens, these charges move back. And now we have equal positive and negative charges. So I'm just going to do this. We have equal positive and negative charges on both spheres. That means the only answer we can use here is both Q1 and Q2 have to be 0. They have to be neutral. So there's no net charge on either one of those spheres. So all we did was brought the rod close and then moved it away. So we had polarization, then we lost it the instant this is then moved. So when you separate the two spheres, they both have a 0 charge. For 20.5, it says metal spheres 1 and 2 are touching. They're both initially neutral, so they both have positive and negative charges. Our charged rod is brought near, so here we go. We've got these negative charges on this side, positive charges then on this side. And now I'm going to separate the two before I move this rod away. So I'm going to leave the rod, it's still positive. I have this negative sphere now. And then I've separated it, and now I've got a sphere on this side which has an excess positive charge. So Q1 is going to be negative. When I get rid of the rod, these charges will just distribute around the surface of the sphere, but it still will have a net negative charge. This one, same thing, a net positive charge. So Q1 has got to be negative, so I know this can't be the answer, this one can't be the answer, and this one can't be the answer. So Q1 is negative, Q2 has got to be positive, so our only answer, and the best answer here, is letter C. So those did go through a polarization, and then once they're separated, those polar charges stay. 20.6, so I have identical spheres are initially charged as shown. We talked about if you touch these two charges, you're going to have some charge transfer. And when you do that, you have to use the algebraic sum in order to figure out what the net charge is going to be. So I'm going to have +4 plus -2, and I'm going to end up with a total charge between the two spheres of +2. Because these charges equally distribute when these two things are touching, so when they are together, okay, they're +2. When you separate them, you're going to have a +1 charge on P, you're going to have a +1 charge on Q. Now we're going to take Q and touch it to R, and when I do that, I get +1 plus -1, and I end up with a net charge of 0 after they are separated. So our only answer that we can answer here for this question is letter C, and that is 20.6. Our next slideshow or our next lecture will be on Coulomb's law, which will be 16.3.